All right, so with this here, we continue driving on information about acids and bases. And yesterday we kind of left off with this. One of the final things that we talked about, we said, well, we called it the auto-ionization of water. Basically, we can break water down into two parts. H3O plus, which is what we called our hydronium ion, and then OH minus, our hydroxide ion. And we said, hey, if you take OH, the concentration, times the concentration of H3O plus or our hydronium, you are going to get this value called Kw. And we called that, or we numbered it 1 times 10 to the negative 14, because that's been experimentally found. Okay, those conditions all occurred at 25 degrees Celsius. 25 degrees Celsius for our acid-base unit will be our standard unless I tell you another temperature. Okay, here we go. pH. We've all heard of pH before. Yesterday you said, or I asked you, and I said, all right, pH is 7, well, that's neutral. Here's a question for you. A pH of 14, is that acidic or basic? Basic. A pH of 1, is that acidic or acidic? So you guys already know the setup of our scale. It's all based or rooted on everything that we did yesterday. Okay? So one thing I do want to point out is this. To find our pH, we use the formula pH equals negative, very important, negative log of our hydronium ion concentration. And just an FYI, that you can also see this H3O plus simply written as just our H plus. In this section, this unit, H plus equals H3O plus. So don't get confused if you see either of those items there. All right, any questions? Anybody still need this? All right, so let's drive on here. Let's make use of this. If we know our H plus, we simply plug that value into our pH formula. So we are given your H pluses here, and we go through this. The first one has an H plus of 1 times 10 to the negative 12. And so to calculate our pH, we take the pH equals our negative log of 1.0 times 10 to the negative 12th. You could put the big M in there if you want. I'm simply going to put it as our parenthesis. And this is all we have to do. Now, again, I'm going to point out you have to start out and you have to put negative log of 1 times 10 to the negative 12th. We press enter, and what's our pH?
1 times 10, or 1.2 times 10 first.
Yes. Can you put it in non-scientific notation? It's the correct answer, but yes.
12.
Yeah, 12. Okay. This is a useful number. Now, you guys already answered a question previously, but answer this specifically here. pH of 12. Is this solution acidic or basic? Basic. You already know this, right? I'll put comma. This is a basic solution. Okay. That's the importance of something that indicates or identifies our pH. Now, same thing here on number 2. I give you a different concentration, but all we have to do is say pH equals our negative log of the concentration 5.6 times 10 to the negative 6. We plug that into our calculator. We say negative log 5.6 times 10 to the negative 6. And I guess because we used 5.6 has 2 sig figs, we round that answer to 2 sig figs. What's our pH become?
5.2, 5.3.
Yep, it would round to 5.3. And based on this number, we just look at that number and I ask you, okay, is this solution acidic or basic? You'd say acidic because it is below 7. All right, so you guys already know the simple process here of acids and bases. We're just going to continue to put a chemistry twist on this. Questions? Anybody need this? All right. So here we go. Now, I broke this next page of notes into a couple different slides, so that way I could have some room to write. But we get POH, okay? POH is going to recognize our base part of the acid and base, and it has a very similar formula, but we see we have POH equals the negative log of the concentration specifically of our OH, or of our hydroxide, okay? Now, I want to tie some things into what we have done, or what we have did in day one notes here, okay? And we're just going to think about how we get to that point and go from that process here, okay? Yesterday we said that if we started out with KW, we said it equals, anybody remember what times what? Yep, I want you to keep that in mind because we're going to use it here in just a second. That 1 times 10 to the negative 14th is equal to our H3O plus times our OH minus. Okay, now here's what we're going to do. We're going to keep extending exactly what you guys just told me. For KW, and I'm going to leave some room on the left, and you'll see why here. KW is actually equal to 1 times 10 to the negative 14. So I'm going to go ahead and replace that with 1 times 10 to the negative 14. And that is still equal to our H3O plus times our OH minus. Okay? Now, we want to make this useful. Other than just copying down the formula or remembering it from the formula from yesterday, we want to make this of use. So here's what we're going to do. We're going to add it, and we can do this as long as we add it, or in this case, multiply it to both sides. We are going to multiply each side by negative log. Okay? So we're going to do this to both sides here by negative log. And I'm going to rewrite this item in red. And so I'm going to say negative log times, and I'm going to put this in parentheses, 1.0 times 10 to the negative 14th equals, and I'm going to break this up here. I'm going to say this. I'm going to say we have negative log times our H3O plus, and then also I'm going to break this up times a negative log of our OH minus. All right. Now, can somebody do this? Can somebody take negative log and put 1 times 10 to the negative 14th and tell me what they get?
14.
Yeah, there we go. So I'm going to write this. Let's write this in green because this is going to be a good formula. 14 is negative log times 1 times 10 to the negative 14th. Okay? This is all equal, and let's just think about this. Instead of writing negative log times H3O plus, if we look back on the previous page, negative log times the H3O plus is equal to what simple letter, 2-letter combination? Go back to the formula. Negative log of this stuff is equal to, go back to the formula. What is it? pH. So we can replace negative log of H3O plus with simply pH. Plus, this is the nature of logarithms, all right? We'd have to ask the math teachers the specifics. I just know how it goes on this. If we take a log times a log and we throw in these signs here, we would end up with a plus, all right? So again, math-wise, logarithms, I can't explain it right here. That's why we have pH plus. no longer do we need negative log of OH minus, but what would that turn into? POH, all right? Now, I want to point out something really particular, and that's my main point here with this slide, is on our AP handout. This is where the usefulness of our appendix and that the AP gives us really comes into play. So right there where it says equilibrium, remember this is acid-base equilibria technically, but you see this formula, 14 equals pH plus POH, all right? So my point is, as we start doing problems, it might be handy just to have that out to go, oh yeah, that formula we went over, it's given or it's not given and I need to do some work here, okay? All right, so let's keep going with this page of notes. Does anybody need this? All right, so here we go. You still got a little bit more. Now, it says calculate the amount of H+, the hydronium ion concentration, with a solution that has a pOH of 10.24. So what we're going to do is this. We first have to start with that formula that we just worked. Okay, so we have to say 14 is equal, do we know the pH yet? No, so we're going to leave that as it's equal to the pH plus the pOH is given at 10.24. So we can have 10.24, and the first thing that I'm going to tell you or ask you is, how can I get perfect? We can subtract. Yeah, let's use red. Okay, so we're going to subtract 10.24 on each side. So 14 minus 10.24, somebody correct me if I'm wrong, should be 3.76, right? Okay, so 3.76 is our pH. And now I just want us to think about this. Our formula for pH, remember, pH equals the negative log of our H plus concentration. So now all we got to do is we got to insert our 3.76 number. 3.76 equals negative log of our H plus. Now, in the future, this will be really easy, but when we solve this, I want to get rid of this negative sign. And you're thinking, yeah, I know how to do that, but it's really important that we do this before we get into our formula. And so I'm going to divide each side by -1. And so if I divide this number on the left by -1, what does that number turn into? Yeah, -3.76. And you're thinking, hey, that really doesn't do a whole lot, but it's really, really helpful because now we have log of our H plus. Now, to get rid of something on one side, we take the inverse. So if you take a look at your calculators, if you hit second in the log button and paint it on values there, it says 10 to the x. So if you hit second and you get 10 to the x, you get 10 root and then a parenthesis. 10 root or 10 to the x is the inverse of log. So what we're going to do is this. We are going to say 10 to the log, 10 root log, which gets rid of this. And in our calculators, we're going to say 10 root negative 3.76. I press enter. I convert my value to scientific notation. And what do we get for the amount of H plus in this solution, the concentration? And let's do 3 sig figs here.
1.74 times 10 to the -4.
Yes, 1.74 times 10 to the -4th, and the unit on that is our big M, okay, for molarity or for our concentration. Any questions here? Anybody still need? All right, we're looking good. All right, so here we go on this. pH, right? We talked about, hey, how could we get to something pH? Well, we got to know the concentration. And so there's some different devices that we can use to get to that point. pH meters, which you probably used before. They use electrochemistry. There's actually a lot of chemistry happening with pH meters. They're really nice, but you have to calibrate them. You have to put them in a specific solution or store them in a solution, so sometimes they can deteriorate. Better for us is pH indicators, which we're going to use quite a bit. Basically, every substance has an area or has a pH, I should say, where it changes from acid to a base. And we really have to do a titration. I don't think I indicate that, but a titration is going to convert an acid to a base in a very specific format. And based on where that changes over on the pH is an indicator that we have to select. Okay, so we got a broad range of colors. We have to select that based upon where does the pH change. And it kind of extends throughout this chapter. All right, questions?
Oh, over there.
Does anyone need it? All right, so here we go. Strong acids, and then we're going to talk about strong bases. I hate in this class to say, hey, memorize this, but unfortunately, this comes down to memorize. All right. Today is going to be pretty easy. We have the strong acids, and then we'll talk about strong bases. If it's strong, we simply plug our concentration of original acid into our pH formula to calculate pH. But you have to be able to identify if that acid is in fact one of these 7 strong acids. If it's not, we can't play by the rules that I'm getting ready to show you. Okay, now, key thing with this. 1, I'm just going to say, hey, flat out memorize this list because it's really, really helpful. But 2, what happens here chemically is nitric acid in this example. HNO3. The H completely breaks apart from the NO3. So in solution or in the reaction, you end up with that H attaching onto water to form H3O plus, and that nitrate, that NO3 with a 1 minus. All of it broke apart. So imagine breaking a stick, right? You break a stick with your hands, and you can't put that back together. It's a one-sided reaction, no equilibrium. Strong acids, no equilibrium. But we have to identify, is it one of our 7 strong acids? Questions? Does anybody need this? All right, so if we have a strong acid, we simply plug the concentration of that acid into our formula. Okay, so I know we just went over this, but the first question you should ask yourself when you come to an acid-base reaction is this. Is our acid, which perchloric acid is what we have here, is that acid one on the one of the 7 strong acids? Yeah, so this is strong. So all you do, if it's a strong acid, is you plug the concentration into our pH formula. So we say our pH is negative log of the H plus, which is equal to the concentration of that original acid. So all we have to do to solve this problem is say pH equals negative log of our concentration, which is 0.040. Okay, so all we got to do in our calculator is this. We got to say this, negative log times 0.040, and let's round to 2 decimals here, or 3 total numbers. What is our pH for this?
1.40 times 10.
Yep. And it just simply, you can just chop that times 10 off there. but we have 1.40. And now think to yourself before we leave this, all right? Does it make sense that a strong acid has a really, really low pH? Yeah, it should. Again, think about the general knowledge you know about pH. Low number pH, acid, strong acid's probably going to be pretty low, pretty close to 1. It can even be, and I should have mentioned this earlier, a strong acid can actually be a negative number. You have to have a really strong concentration, but it can be negative. So oftentimes we can find pH from 0 to 14. Really, really basic substance can be over 14. It can be 15, 16. Really, really acidic substances can be negative pHs. You don't think about that, but it actually can. All right, so questions? Anybody need this? All right, now, strong bases. Again, the only way to know that if you have a strong base or not is if we have identified these strong bases. Now, there's a few more than 7. There's 11 strong bases. What I like on strong bases, at least in my mind, is number 1, everything is a hydroxide. OH. You see OH, OH, OH. Number 2, you have some identifiers. The first list here, you look at lithium all the way down to francium, they're in group number 1. Now, hydrogen's in group 1, but we don't include it in there. Everything there is a strong base. Heavy metals start with magnesium. Magnesium hydroxide is considered a heavy metal. If you put your finger on group number 2, magnesium, you went all the way down the rest of that group, you would end up at radium. Okay? That's how I memorize it, is based upon the group. All right? Questions? Once more, strong bases completely break apart. Think about the stick example. So sodium hydroxide, all of the sodium separates from dihydroxide. All right, one single reaction arrow. No going backwards here, no equilibrium. Anybody need this? All right, here we go. So this should say, what is the pH of a 0.028? And that should be a big capital M here. We'll make sure we indicate that. That should be a big capital M right there. What is the pH of a 0.028 molar solution of sodium hydroxide? So the first thing to do is look at what you have. And you ask yourself, okay, sodium hydroxide, is that a strong base? Yeah, this is strong, and it's a base. So what we have to start out, because it's a base, we can't jump right in and we can't find directly our pH because OH breaks off. What we can find first is our POH, and it is equal to the negative log of our OH minus concentration. Now that OH minus concentration is equal to the concentration of our solution. So all we have to do here is say, all right, PaOH equals negative log of our 0.028 molar solution. Okay, so we plug this into our calculator, and then we do this. So negative log 0.028. We close the parenthesis here, and we get a POH of 1.55. Okay, we would plug that back into that formula we started a couple sections ago or a couple pages ago, where 14 equals, do we know the pH yet? No. So we say pH plus that number that we just found, which was 1.55. So again, how do we get pH all by itself? Subtract that 1.55. And so if we take 14.55 or 14.0 minus 1.55, our pH ends up being 12.45. All right, any questions?